time for us to talk about error analysis. Now, if you hear the phrase error analysis and you're an engineering type person, you might be thinking something along the lines of a robot doing something like error, does not compute. But what we mean by error analysis is saying, look, numerical integration, in this case, is about an estimation. And of course, estimation means you're off. There's an error. And what we want to do is say, how big is that error? But really what we want to do is say, how can we make sure our error is sufficiently small? Because it's important in some cases that we have to say, we need to make sure our approximation is good. And so how do we know if it's good? How can we bound our error in a reasonable way? So that's what we're doing. Now, as you go through and do practice, it's important that you do as much as you can on your own. So if you're following along with the video, make use of the pause button. If you see a problem, try it yourself first, and then of course we can always compare answers later. Well, let's begin. Our first problem. Suppose we know that the second derivative is at most 6 between 0 and 2. Then how many steps should we choose for the trapezoid rule if we want our error to be at most 0.00001? Okay, now you might say, well, steps, what does steps mean? Well, really, when we're talking about steps, another way this could be phrased is subdivisions. How finely do we need to chop? In terms of our formula, that's n. So in other words, say, look, we want a small error. We have a function. Do we need to have a fairly small number of n? That would be saying, look, you don't need very many n to get a good approximation. Or do we need to have a large number of n? Which means, look, because there's so much variance, we have to keep our error in check, so we need many, many pieces. All right. Now, the good news is there is a way to do error analysis for the trapezoid rule, and there's a formula. And it says E sub t. And the way you should read this is our error in the trapezoid rule. Now, how do you find the error? Well, when you talk about the error, you say that's the estimate versus the actual. So you take the difference, and here it's the estimate from the trapezoid rule. So this E sub t is they take the estimate from the trapezoid rule, subtract the actual, and take the magnitude of it. And we want that to be small. So what do we do? Well, we say our error, we want to have our error is at most 0.0001. And so we say, aha, we know that this is an upper bound for our error. So we are going to take that expression and we're going to just slide it into there. So we can say, look, if we can make m times b minus a cubed over 12n squared less than 0.001, then what's going to be true? Well, then it has to be true that our error is also less than or equal to 0.001, because that's what the inequality gives us, because this is greater than or equal to our E sub t. Now, in our case, what does m measure? Well, it's measuring just how much the function fluctuates. And so in our case, it's a measurement of the maximum value of the second derivative. So that's what this part here is saying. M is a bound for how much the second derivative changes on our interval. So it's told to us that m here is 6. So that's good. That's great, actually. It makes our problem pretty straightforward. We say, okay, we have all our pieces in place. So what do we need? We need to have the following. 6, which is our m, times 2 minus 0 cubed divided by 12n squared has to be less than or equal to, now 0.00001. Well, let's write that in a little bit nicer way. See, that's 1 over a big number. Well, how big? Okay, let's just count how many times we moved the decimal places over. We moved it over 1, 2, 3, 4 times. So if we did that, that's divided by 1 over 10,000. That would be how you move the decimal place over 4 times. Okay, well, great. Now, let's take both sides and turn it over, because our goal is to get a bound on n. So we're turning both sides over. And also, notice this is 6 times 8, which is 48. Here it's 12. So when we flip it over, and if we simplify, since 12 goes into 48 4 times, we'll have n squared over 4 is less than or equal to 10,000. Or, when we flip, what happens to our inequalities? It's greater than or equal to. Because when you flip, you got to reverse your inequality. Or n squared has to be greater than or equal to 4 times 10,000 is 40,000. Okay, now on a side note, 40,000 is the same as 200 squared. Now, finally, we say, okay, take the square root. And if we do that, we say, aha, if n is greater than or equal to 200, that is sufficient. All right. Now, a couple things. You might say, well, wait a second. Couldn't we have chosen negative? And the answer is, no, we can't. Because n is a number that we're splitting our interval from a to b into. I can't split a to b into negative 20 different pieces. That doesn't make any sense. So n is a positive quantity. There's another thing, though, that's a little bit more subtle, and I want to talk about it for just a moment, since we have time, and we're among friends, so we can have this discussion. Now, does that mean that our error is going to become 0.0001 at 200? And the answer is kind of. What it says is definitively, absolutely, if you take 200 and subdivide it, interval from 0 to 2 into 200 pieces, you're guaranteed that your error is at most 0.0001. It's possible that because of the shape of your function, you might have a smaller error than 0.001 sooner, but the error analysis that we are applying does not guarantee it. So you might be okay if you just went with n equals 20. I mean, it's possible. But what we're after is, we don't just want to say maybe. It's not like maybe, we'll make it to the moon. There's enough gas. No. We want to say, look, we definitely want to get to the moon. How much do we need? Tell us. We need to know. And so we're after definitive. When for sure are we safe? And the answer is by 200, any number above 200, you're good to go. Now you might think 200, wow, that's a lot. And yeah, it is. So this is where it comes in and says, aren't we glad we have computers? Now, back in the old days, we had computers as well, but they were actual people who would just sit there and just work all day doing very simple computations. And of course, nowadays we have mechanical computers have turned into electronic computers who are a little bit faster, hopefully also less likely to make mistakes. Hopefully, but who knows? All right, well, let's keep going. Our next problem. If the fourth derivative is bounded by 90 in the interval from 0 to 2, then how many steps should we choose for Simpson's rule if we want our error to be at most 0.00001? Okay, good. Now, very similar to the problem that was just done, what do we see? Okay, again, steps. It's just another way of saying how many places do you want to subdivide. And one of the things you'll discover is as you go further and further into math, a lot of people have their own terminology for things. You want to be a little bit flexible because people use different phrases. And so think about what do people mean. Oftentimes, it's the case that two people are talking and they're trying to explain to each other what's going on. And it turns out they're both saying the same thing, but using different words. And so it can be a little bit challenging the further you go. Okay, so the good news is we have a formula. It says, look, if we're looking for our error in Simpson's rule, and again, this is our difference between our actual and our estimate. So that's when we talk about error, it's saying compare the two pieces. Well, it's bounded by this quantity. So as before, we'll have our error in Simpson's rule. That's what the S is there for Simpson's. Well, what we can do is we can say, look, we want that to be less than or equal to something. Well, we know already that's less than or equal to this quantity, m times b minus a to the fifth over 180 times n to the fourth. So if we can make this quantity small, then that quantity is also small, almost for free. So we can say, look, we'll just make sure that that's small. So that's less than 0.0001. Now we have sort of the same process as before. It's like, okay, we want to make this small, plug in what we know. This m is a bound for the fourth derivative, which is why they started by saying, oh, hey, we can bound the fourth derivative. So we have 90. B minus a would be 2 to the fifth, divide by 180, and to the fourth. We want that to be pretty small. Well, notice 90 times 2 would be 180. So we can do a little bit of cancellation pretty early. So we could say, look, this 180 cancels with a 90 and one of those 2's. Now, flip both sides because we really are trying to find n. And we say, okay, look, n to the fourth divided by 2 to the fourth is less than or equal to, well, 1 over that number. What's that number? What's that number? Well, the way to figure that out is say, okay, look, it's like you took 1 but moved the decimal place. How many times? Well, 1, 2, 3, 4. Okay, so every time we move the decimal place, it's like dividing by 10. So it's like we divide by 10 4 times. So I can say, hey, this is the same as 1 over 10 to the fourth. So if we flip, what do we see? Well, that's less than or equal to 10 to the fourth. All right, well, good. So n to the fourth is less than or equal to, multiplying the 2 to the fourth across, 2 to the fourth times 10 to the fourth is 20 to the fourth. And, I did it again. I forgot, right? When you flip, your inequality has to change directions. Now, I could spot that something was off because, well, it's me. I know I make mistakes like this. But I also was saying, I'm going to get n below something. When you're doing error analysis like this, you say, n has to be above something. Because the idea is the bigger the n, the better the estimate. So you want n to be rather large. So if you're like, n should be below something, no, you made an error. Okay, our error was we took our inequality the wrong way. So n to the fourth has to be greater than or equal to 20 to the fourth. Well, what does that say about n? Take the fourth root of both sides. And now n has to be at least 20. But you'll notice something. 20, it's not too bad. It's actually a relatively modest number of things to take. Almost within the realm of what we'd be willing to do by hand. Almost. And if you compare it, of course, to Simpson's rule, now these don't compare directly. If you compare Simpson's and trapezoid, generally speaking, you'll see that there's a lot more places or a lot more steps you have to do in the trapezoid rule, but that's because you have an n squared versus an n to the fourth. And that can really help you. So it shows you the power of Simpson's rule. Where it says, look, you can capture quite a lot with a relatively modest investment. So, all right, well, on to more problems. Okay, next problem. Suppose we want to use the trapezoidal rule to estimate our integral from -1 to +1 of 3 cosine squared of 2x minus 5. And the question, find a number n of trapezoidal strips for which the error is at most 10 to the minus 4. Okay, cool. And they even gave us the formula here. See, we're not trying to test you right now on memorizing the formula. We really just want to be comfortable with how do we use the formula. All right, now, we are just after what? Well, our answer is a number n, and that's what we're after. And so one thing to keep in mind is we don't need to know what is the value of the integral. We could, this is one we could do, but we don't need to, and we don't need to do our estimate. And again, that's not what we're after. Our goal here is saying, how many terms do we need to go until we're comfortable that the value we get out is within this amount, within 1 over 10,000. So, what do we need? Well, what's the difference here? We did some problems like this a little while ago. The difference is now it's really, we don't have a bound given to us for m. So we got to spend time here on what is m. We know m is bounding the second derivative. So that's where we're going to be spending the time on this problem. All right, so here we go. So our function is 3 cosine squared of 2x minus 5. Now, we could start taking derivatives now, but we know we have to take 2 of them. But another thing we can do is say, hey, hold on, is there a nicer way to write this function? Now, you might be thinking, wait, why would we do that? Well, remember, one of the important things about our work is that we really love ourselves, and we really want ourselves not to have to do anything too crazy in terms of computation. And so one of the things we do is we kind of have that floating in the back of our mind, the question of, hey, could we simplify this expression? So when we have things like logs tend to simplify pretty well, and trig also tends to simplify pretty well. In particular, the square says, oh, I could reduce it by power reduction. So if we apply power reduction, we could say cosine squared, well, that'd be a factor of a half, and then it'd be 1 plus cosine of double the angle. So 4x minus 10. All right, so I took this cosine squared and I replaced it by power reduction by something a little bit easier to work with. So why do I say that? Well, let's take a look at the derivative. That constant goes away. So it's 3 halves. Derivative of cosine is negative sine 4x minus 10 times root of the inside, which is 4. And that's it, right? There's no like, oh, the 2 comes down, then there's a cosine times a sine, and it starts getting bigger. Nope. Because we simplified it, the derivative is simpler. How about the second derivative? Well, there's a negative 3 halves. Derivative of sine is cosine, 4x minus 10. Then there's a 4 from the chain rule, but there's also a 4 from what was in there before. All right, so what do we end up with? Well, 3 halves times 4 times 4. Well, that's really, right? 2 goes into 4, so it's really 3 times 8. So you end up with negative 24 cosine of 4x minus 10. Okay, so there we go. That's our second derivative. Now, what we need to do is bound it. And so we ask ourselves the question, what can we say about the magnitude of this expression, negative 24 cosine of 4x minus 10? Now, in particular, we want to say for negative 1 less than or equal to x less than or equal to positive 1. There is a tendency for people to say, oh, let me just look at the endpoints. But that's a dangerous thing because it's not guaranteed that the largest or smallest values are obtained at endpoints. But let's just think about what we have. Certainly we have the 24. What about the cosine? What can we say about cosine? We can say it's a bounded function. Remember, cosine, it oscillates. What does it oscillate between? +1 and -1. So we can say, hey, this is at most the 24, because the cosine can't make it bigger. And so we can say, aha, our bound is 24. So there's our M. So all our pieces are in place, ready for us to go. So here we are. We want our error, which is bounded by this quantity. Now look, I can replace what M is. M is 24. 24. B minus A. So that's from here. A to B. So that would be 1 minus 1 cubed over 12 and squared. So if we want that to be small, it suffices to make that small. So in other words, if we want our error with the trapezoid to be small, this term can be small. And we want to say, okay, let's make that less than 1 over 10 to the 4th. Okay, well, we can simplify, right? We say, okay, 12 goes into 24, that's 2. Then we have what? 2 times 2 cubed. So we have 2 to the 4th over n squared is less than or equal to 1 over 10 to the 4th. Flip both sides. N squared over 2 to the 4th is greater than or equal to 10 to the 4th. That would do it. Multiply across. N squared is greater than or equal to 2 to the 4th times 10 to the 4th, 20 to the 4th. Well, okay, take the square root. And that says, look, n is greater than or equal to 20 squared, or 400. So, by the time we chop up into 400 pieces, our error is guaranteed to be within 0.00001. Good. Now, it might happen sooner, but definitely by the time we hit 400, and if we do anything past 400, it's even better, right? Should be an even better approximation. All right, well, one more. Let's do one more problem. So, recall that the error in Simpson's rule, there's a nice formula for it. It's this m over b minus a to the 5th divided by 180 n to the 4th. And m is the maximum of the 4th derivative. All right, so we want to use this error estimate to bound the maximum error for this integral of what? Well, we're going sine of 2x, so we want to estimate the integral of sine of 2x dx from 0 to pi over 2. So that's our goal. Now you're probably thinking, well, we don't need to estimate it, we could just compute it. Well, I know we could, but right now we're doing our estimations. We're learning to do things with some functions where we can actually find the exact values, so that we can also learn to do things with some functions where we can't, so that's all right for us. Okay, so that's our goal. And we say, okay, what do we need to do? Well, we want it to bound the maximum error. Well, that's fantastic. We say, look, our error with our Simpson's rule is going to be bounded above by this expression m, then b minus a, so that would be pi halves minus 0 to the 5th, divide by 180 n to the 4th. But we're even told how many intervals. So we know the number of intervals here, so 20 to the 4th. So we're basically done, right? Because we want to say we want to get an error estimate. Well, really, we want to bound the maximum error. If we knew the error estimate, we'd actually know everything. So when we talk about error analysis, we're really bounding what our error could be. So all of the work here is going to come down to, what is m? So let's figure that out. Okay, so we look at our function. Well, we need to look at the fourth derivative. So m is the max of the fourth derivative. So we say, okay, f of x, that's sine of 2x. And so we just start taking derivatives. The first derivative, well, that's 2 cosine 2x. The second derivative would be minus 4 sine of 2x. The third derivative would be minus 8 cosine 2x. And the fourth derivative would be 16 sine of 2x. Now, what do we want? Well, again, the question is, what can we say about this function, 16 sine of 2x? And we're going from 0 up to pi over 2. If you only looked at the endpoints, you'd say, oh, plug in 0, you get 0. Plug in pi over 2, you get sine of pi, which is 0. Hey, 0. Beautiful. But you can't just do that. Remember, we have to take into account any point in between. But again, we say, look, sine is bounded. It goes between positive 1 and negative 1. And therefore, this is less than or equal to 16. That's m. When we talk about m is a number. So m is a number here. It's not a function, it's a quantity. So it's something that we're bounding by. And now we're basically done. Why? Well, look, we just plug in. We have 16, and then we have what? Pi over 2 to the 5th. Then we have 180 times 20 to the 4th. And you'll notice it said you don't have to simplify, which is great. Woohoo! We don't have to simplify. Now, we could simplify a few things. So, for instance, what do you have? Notice there's a 2 to the 5th, which is 32. There's a 16 over 32, which if you simplify, would leave you with just a 2, which you can move downstairs. That's with the pi to the 5th upstairs. Then you have a 2 times 180 times the 20 to the 4th power. And if you look at that quantity, you'll notice it's a pretty reasonably small quantity, which means it's a reasonable estimate. In other words, we're going to have a really, really good grasp of what that number should be. So there you go. And really, most of the work in error analysis is trying to get a good handle on this quantity where you bound some derivative. So you can imagine all sorts of questions where it says, well, what can you say about the bound for m, or find the bound for m, and then just everything else is what it is. And there you go. There you go. All right, well, thanks for coming, and hope to see you again at some point in the future. Bye.